Wow, what an intro that was. Clearly all the budget went there. But yeah, recently I have made a post on YouTube asking you for different topics you'd like me to explain. And right away on the very beginning I saw EPR. And you know what? I already knew this was gonna be a winner, okay? EPR is a really niche technique, but it just so happens that on the Discord server I have someone who's very much an expert on the topic. It's really often overshadowed by NMR, but wouldn't you believe it, he just happened to have done both. So it's very convenient, and I went in, before even contacting Flame, I did a whole bunch of research on electron paramagnetic resonance spectroscopy to make sure that this video is gonna be great, and as such, I'm absolutely ready to...
Isn't that the EPR paradox?
What?
Well, in the common they mention EPR paradox.
Paradox, like the Einstein-Podolsky-Rosen paradox, the quantum mechanics thing, the theoretical physics. Yeah, no, sure, why do I even bother? So, the EPR paradox. In retrospect, I should have waited, actually, instead of picking one of the first comments, because EPR paradox is pretty advanced. It's pretty difficult to grasp, in fact. And so, the days I have spent delving into this topic, they weren't exactly fun, but I do believe I have a pretty decent way of explaining it, because the idea is simple. Einstein just had beef. Einstein was never a fan of quantum mechanics. Despite being one of the accidental fathers of quantum mechanics, he never cared for it. Relativity was his big love, and quantum mechanics was the bastard son that he despised. But still, it was crucial at the time. I mean, quantum mechanics was the new kid on the block getting all the things done, and Einstein didn't exactly like that. God does not play dice with the universe and all that jazz. So he, along with a couple of his buddies, made an argument. The EPR paradox, basically trying to showcase just how much quantum mechanics sucks. And that's what we're going to be talking about today. But first, we need to discuss kind of Einstein's background a bit, you know, because he's kind of trying to go against a new emerging field of science, a new emerging field of physics, so he better have some pretty good reputation to back that up. So first we need to obviously delve into what Einstein has kind of done up to that point. And I'm certain it won't be too convoluted, it won't be too complicated, it's just gonna be... Relativity, huh?
First, let's start by imagining a universe with the x direction, the y direction, and some objects in it, like so. Now let's evolve this universe as follows. Great. I don't think I need to explain it, just your garden variety to the universe. Or actually, is it? Keep in mind we have time, so our space-time will actually be 2 plus 1 dimensional, which means that we can represent it as a 3-dimensional universe, where this plane represents space and this direction represents time. Great, this is our standard 2 plus 1 classical universe, but we're not here to be classical, we're here to be general and relativistic, so we need to account for one more thing, and that is curvature. Basically, in classical mechanics, we can picture our universe this way, and then we can take a single slice of it, and there, this gives us a moment in time, simple as it could be. In GR, however, this moment, in quotes, can be curved. This really messes with a lot of things, which is why we won't get into it right now, and instead I'll just mention that it creates the metric, or for Americans watching the video, the imperial, which gives us things like a notion of past and future, distance, proper time, long story, gravity, causality, and finally, the speed of light. So, light always travels at the speed of light. That's what Einstein said. Really, somebody give that man a Nobel Prize. No, but seriously, the speed of light is a bit of a misnomer, because it describes something very important. It describes the speed limit of a massless object. So basically, objects have mass, and that mass tells us how difficult they are to accelerate. This is a bit of an annoying equation to describe, so instead we'll go with a simplification of 1 divided by m. That is, the ease at which our objects accelerate, so as our mass goes up, it becomes more and more difficult to accelerate our object, which means that if we naively went with the F is equal to ma as our equation of choice, then if our object has more mass, we need more force to accelerate it to the same acceleration. Okay? Pretty intuitive. Heavy things are harder to move, that's basically what I'm saying. So here we have the graph of acceleration in relation to mass. As the mass goes up, the acceleration goes down with the same force. Okay, so if you have a massive object, with the same force it will accelerate less. And that's all great and good, but what if we start decreasing the mass? Well, then with the same force our object will accelerate more and more and more, and eventually it will reach infinite acceleration. Now, keep in mind once again that we're dealing with a major simplification of what GR is here, so this isn't the proper equation, not even close. And saying that it equals to infinity is also mathematically a bit inaccurate, and trying to figure out what it means is wrong on so many levels, so we're doing a simplification, but it's fine because it actually brought us to the correct point. This infinite acceleration basically means that, no matter the force, it will instantly accelerate to maximum velocity. Or, in other words, it will always be traveling at maximum velocity. So if we had, and purely hypothetically, right, just bear with me here, some kind of massless particle without mass, then it would always travel at this maximum velocity. And even better, if that velocity was measurable, if we could measure it, keep it as a constant and name it after the particle, then we would actually have a pretty neat system. So if, once again, purely hypothetically, that particle was a photon, particle of light, we'd call it the speed of light. And there we go, the speed limit of the universe. Now, you may be wondering, make it, how can the universe have a speed limit? And to answer that, I would have to make a separate video about special relativity, so let's keep it for later. Anyway, let's review what we've got so far. We started with a universe and slowly introduced more and more concepts from relativity, which eventually led us to a constant maximum speed of the universe. And the reason why it's important is because no object can ever travel faster than that speed. This is the speed that an object reaches once it has nothing more slowing down its movement, the maximum limit. And it will be important in a second. But before we talk about that... This video is sponsored by no one. Yes, no one is sponsoring me, don't worry. But if you don't mind me taking a minute of your time, I would like to mention that I have been trying to register a charity for the past 6 months. I don't have enough time right here in this video to go into it. On the second channel, I kind of am giving out updates about how this is going, and also on the Discord server I'm giving out these updates, but doesn't matter. The thing I want to mention is that in the process of setting up the charity, I went broke. This month, the bills from my normal life, as well as the bills from the charity, lined up to the point where I spent a couple of days without being able to buy food because I didn't have money. So I would like to avoid that for the future, and so as such I'm trying to get minimum wage on Patreon. I know, crazy high goal. So if you are in a position where you have some disposable income, I would really appreciate that if you went to Patreon and donated some money. You'd get some symbolic perks for it, like, you know, early access to the videos. For example, the first chapter of the carousel video is already on Patreon. Second of all, you'd get like a Discord points on Discord in the bot that I made, long story, but yeah, that's the basic idea. If you are in a position, I would really appreciate that. Anyway, back to the video. What are we talking about? This all has nothing to do with the EPR paradox. Well, that's not exactly true. It has almost nothing to do with the EPR paradox, but I still wanted to lay it down as the groundwork to show you how Einstein thinks. You see, Einstein is a little bit of an overrated physicist. That's not because he wasn't brilliant. Oh, he was a genius, revolutionized the field. It's just that for most people, he was kind of the only physicist. For most people, Einstein is the only physicist they know. And that right there is kind of
problematic because it brings him up to this kind of mythological figure, which he wasn't. He was definitely one of the greatest physicists of all time, but he had a perspective and outlook on physics which wasn't objectively true. It was subjective. It's what he thought of physics, and that outlook was very real, very core rational. Einstein's style basically revolved around taking a simple idea and then taking it through its limits, through usage of extremely rigorous and professional mathematics. I mean, the fact that speed of light is always the same is a pretty difficult thing to wrap your head around, but if you propose it in a way that general relativity proposes it, or special relativity, it becomes kind of simple. But a much better example of that is the whole information bit. You see, Einstein had this idea that, I am paraphrasing here a bit, information can't travel faster than the speed of light. And the reason why is because, as I previously mentioned, nothing can really travel faster than the speed of light. Speed of light is what you get when you have the easiest possible path. And you can't really get easier than easiest, so speed of light is the limit. Which means if you want to move something faster than the speed of light, you can't. You're getting into some really wacky physics territory, imaginary mass tachyons and all that jazz. In real reality, if you have something, either that something has no mass, at which point it will travel at the speed of light, or it has mass, in which case it won't travel at the speed of light. It will travel much, much slower. And so that's the idea, that's the setup. The basic idea being that if you have something, then certain rules apply to it. And for example, something cannot move faster than the speed of light. Oh, there we go. Pardon the stretch. That's the Einstein side of the story. Pretty simple. Now next, in order to get to the EPR, we'll need the paradox itself. And that I'm pretty certain will require just...
Okay, so what is the core of the issue here? What is the problem the paradox is trying to solve? Well, let's imagine a particle. Heck, actually, let's imagine two particles. They are described by two different functions. Entanglement is when you describe them as a singular function that cannot be broken down into two separate functions. That's kind of what entanglement is. Now, if our particles are not entangled, then we can just have one of them, figure out its wave function, and then we'll be able to know the value of the wave function at different points. But we won't be able to know the value of the wave function of the other particle. Makes sense. If, however, they are entangled, then if you figure out the wave function of the first one, you know the wave function of the second one. So if you know the first one, you know the second one, and this leads to problems. Because if we place our first particle somewhere and the other particle 300 light years away, then if you figure out the first particle, then you know the second particle instantly. Okay, once again, this is not actually what happens, but I'm trying to explain a really difficult topic here, so I'm simplifying what quantum mechanics is and not going into states as vectors because that's unnecessarily complicated. Basically, I don't want you to focus on the wave function nonsense too much because that is nonsense simplification. What I want you to focus on is this. If you have two entangled particles, measurement of one of them gives you measurement of the second one as well, which is a problem. So Einstein's issue with this entangled state is as follows. If you have your particle, you measure it, then there is no issue. But if it's entangled, however, this measurement affects the other particle. So in order for that to happen, something had to travel from the first particle to the second instantly. Or in other words, faster than the speed of light. But how could something be faster than the speed of light? As I mentioned, light travels at infinite speed already, basically, so how can something be faster? What is it? Infinity times 2? Infinity squared? What is the mass of an object that's less than 0? That's the problem, that's the paradox. We moved some objects instantaneously, and that is an issue. So, to rephrase it, because I really want to make sure you understand, what Einstein basically is saying is that these particles have some element of reality in them. For example, if you're measuring the spin of the particle, then Einstein believed that the spin of the particle existed, hidden away under all the complexity of the particles. If you measure one of the particles, in order for the other to be affected, something had to move from the first particle, the element of reality of the first particle, to the other and change it. And that something has to travel way, way faster than the speed of light, which is impossible.
And so yeah, that's the argument. If you understood it, congratulations. That's literal quantum mechanics, and not even basic kind of quantum mechanics, just genuine, proper, difficult quantum mechanics. If you didn't, don't beat yourself up too much for it. As I mentioned, it is quite difficult, but the core of the argument is actually really simple. If you have two particles, you can entangle them so that one particle gets kind of connected with the second one. They both become like a singular object in a way. Don't think about it too hard. The point is that once you have that singular object split in two, you can move them apart, and no matter how far apart you move them, no matter how far apart they go, they stay linked together. One of them affects the other affects the first one. So if they have some kind of property, let's for example consider spin, because it's the most classical of examples, then measurement on the first particle of spin will cause the second one to collapse. If you measure the first one as spin up, the second will be spin down. That's the idea. Or in other words, to really drive the point home here, if you have a particle that's entangled with another particle, you measure the spin of the first particle and you get spin up, that means that the other particle will be spin down, even if it's 300 light years away. Or in other words, the measurement of one particle affected the other particle. One particle, which is 300 light years away, got spin up, and the other particle, on the other side of the universe, if you want, gets spin down. You have affected something not even faster than the speed of light, at an arbitrary speed. You have done something simultaneous at an arbitrary distance. You have moved something from place A to point B, linking those two places in space-time together instantly at an arbitrary distance. It doesn't make sense. You can't do that. What have you moved? How have you moved it? It's a paradox. We know that the principles of relativity work, and this breaks them. This allows for so many problematic things, anything from very subtle changes to very radical ones, like time travel. So yeah, this entangled state cannot exist, and as such, quantum mechanics cannot work. It's a fake field and will never go off. Wait, was that? No, I'm just kidding. Actually, the resolution of the paradox was genuinely the easiest thing to research, because that's just an entangled state research, and that's pretty simple. The setup to the EPR was genuinely more difficult than the resolution, because the resolution is surprisingly elegant.
In order for us to find the resolution of the paradox, we need to switch from this hyper-relativistic causal view of the world into a more probabilistic quantum mechanical one. So, what is a particle? Well, a particle is just a state which describes its probabilistic nature, so you can think of it as an esoteric blob of what could and would be. Now, onto this state we can impose a measurement, and from this state we can measure some kind of value. And once we do, the state collapses into a value we can actually use. So, if we're measuring something like a particle that has something like spin, before you make your measurement, the spin kind of doesn't exist. The particle has all spins and no spins at the same time. It's just a blob of nothingness, and it's our measurement that gives its value. So, with that in mind, let's consider the experiment again, this time with a quantum mechanical viewpoint. We have two states and they are entangled. What this means is that you have your system of two particles and you can't just describe it as the first particle with the second one, only you need to describe it as both of them at the same time. Now in that kind of system, if we perform our measurement, they both collapse. But nothing has to travel from the first particle to give the value to the second. No information has to be moved, nothing has to violate causality. They just have the value now. There is no element of reality, nothing underneath, just quantum mechanics. And an important thing to mention here is that Einstein wasn't really trying to destroy quantum mechanics as a theory, because that's the viewpoint I've really often seen portrayed, and that's not actually true. Einstein was just arguing that quantum mechanics is incomplete, which, I'll be honest, that's fair, because it is incomplete. We still are yet to create the theory of everything. But this misunderstanding hides from a very important point, that Einstein was still wrong, and very wrong at that. He wasn't wrong because he was trying to destroy quantum mechanics, as I already mentioned, he wasn't. The reason why he was wrong is because he thought quantum mechanics was incomplete because it lacked that inherent hidden value, that element of reality. Because the spin got created upon measurement, not beforehand. It wasn't always existent, and experiments proved him wrong. So, no, Einstein didn't actually have the beef that we really often attribute. But at the same time, he wasn't correct. He was wrong. And so that's why it doesn't really matter how smart you are. It doesn't really matter how much of a genius you are. If the one who disagrees with you is the universe, then you are gonna end up wrong. So there we go, so we have the post, and then in there we have sounding sound waves would be fun, that would be tempting, apparently it's very visualizable, at least that's what Remco told me. Explain how carousels work soon, Adrian, soon. You could talk about the EPR paradox, that is precisely the topic I picked. Just tensor, but you might have explained that in the video. Tensors would be brilliant, in fact they would be so brilliant that I'm gonna leave them for another video. Explaining torque, that's tempting. Also, I would be tempted to do something more classical mechanics, because I tend to talk about these complicated, like relativistic, quantum mechanical. Would like something more engineering-wise, something more classical mechanical. That would be a nice change of pace, so I like that. Adding and subtracting may seem funny, but going from sets to fields will be included in the same video as tensors, so that will take me a solid hour just to get there. Let's make it that for later. We'll see a video about nuclear fusion. That's also nice. I haven't really done many videos about nuclear physics. That's tempting. Blackbody radiation. That's thermodynamics. Not quite, but sure. Aharonov-Bohm effect. That's a curious one, because apparently it makes like particles have electromagnetism with no field. It's weird, so that's a maybe, but I don't know much about that. I would need to do a lot of research. Joins the members 3 and 2. We don't know exactly what joins the members are. Tally Hall, yes, Juno was mad. Trajectory equation, once again, that could be interesting. I feel like that would have some really nice visualizations to go along with it. So yeah, that's tempting. Leave your suggestions for more topics in the comments, and I'm gonna pick another one for the next video. Thank you very much for watching, and have a great day. Bye.